So now that we've read about the pooling, so let's see what it actually looks like in practice. We had this study published in the Archives of General Psychiatry, riveting reading, I'm sure, in March 2001 that examined the impact of depression on a patient's ability to survive cardiac disease. Researchers identified 450 people, doesn't say picked them randomly, or they picked them randomly, and evaluated them for depression and followed the group for 4 years. Of the 361 patients with no depression, 67 died. Okay, that sounds like a p-hat to me. So how about let's jot that down. I'm going to just find a place in the margin. You should do the same. So I'm going to write down p-hat, and those were the people with no depression. So I think I'm going to call that p-hat with an N for a subscript for not depressed. And that was 67 out of 361. So technically that's successes, even though, dying really doesn't sound very successful. But that's what we're studying, are the people who actually died from the cardiac disease who were not depressed. Now, as a decimal, that's about 0.186. So we lost about 18.6% of those people to cardiac disease. And then we'll keep reading. Of the 89 patients with minor or major depression, 26 died. So that's a second p-hat. Maybe we'll call that one p-hat with a subscript of D for depressed people. And, bless you, 26 out of the 89 died, which comes out to about 29.2% as a decimal. So at first glance, does it look like the people who are depressed may be more likely to die of cardiac disease than the people who aren't depressed? Yeah, about 10% worth, maybe a little over 10%. 10.5-ish. So the question then is, among people who suffer from cardiac disease, are depressed patients more likely to die than non-depressed ones? Well, it seems like there's probably something going on, but I can't really argue that 10.6% difference is statistically significant unless I have some standard error worked in to see how big that difference really is. So we're going to need to run a test. Now, a little review question before we get into the actual testing. We picked some patients and followed them for 4 years. So we studied them after we picked them. There's a name for that kind of study. Do you remember what it is? You're close. Prospective. Spect is that Latin phrase for to look. So prospective study. Since we're getting, we're down to 40 days from the exam now, every little bit of review stuff that we can kind of work in is going to help us in the long run, so we'll be squeezing in some old terminologies along the way just to kind of keep it fresh. So we did a prospective study, which means we can't argue any cause-effect, but we might be able to find some association between depression and death from cardiac disease. That's what we're looking for. So let's scroll on down here to writing our hypotheses. Okay, so before you write hypotheses, and most of you are doing a beautiful job of this based on the one proportion test that we've done. A couple of you straggling and want to skip to the hypotheses, you need to define your parameters first. So there are two parameters that we're wanting to look at. The proportion of people not depressed and the proportion of people depressed in the population. So let's say that P sub n is the percent of non-depressed patients who die maybe I should squeeze in all non-depressed patients who die, because this is a population parameter. Do not put a hat on this puppy. We know what the p-hat is. We're hypothesizing about everybody with cardiac disease. So make sure that doesn't have a hat on it. And then P sub D is the percent of all depressed patients who die from cardiac disease. Okay? So you need, for your own sake, to have it straight in your head what those p-hats mean. And on the AP exam, if you put hats on those, or if you put hats in your hypotheses, you will get 0 points for your hypotheses, because you're indicating that you don't know the difference between a population and a sample, and that's big time trouble. That's a big misunderstanding. Okay, now let's get to the hypotheses. So H naught, what do we want to suppose about these two different populations? They're equal. Okay, so we could say P sub n equals to P sub d, but we really need a number. We need to see a difference. I'm a creature of habit. I like to put my bigger number first. And I'm trying to show that the depressed people are more likely to die, so I'm probably going to put P sub d first and then subtract P sub n from it. Although you could switch that up if you want to. It just means you got to change the direction of your inequality in your alternative. But I'm going to argue that the depressed patients and the not depression patients, if they die at the same rate, because I always want to assume that they're the same in the null hypothesis, that difference should be 0. Now the good news is that difference is always 0. We always assume they're the same. Therefore the difference is always 0. So that's a cookie cutter first piece. It always works that way. Then the alternative tells something different about that difference, P sub d minus P sub n. I'm trying to show that depressed die more often than non-depressed. So that means this should be a bigger number minus a smaller number, which means I should get what kind of number? Positive. Positive is greater than 0. So this is a one-tailed, upper-tailed test because we are out to show or look for evidence that depressed people die more often. Okay? How are we doing so far? Easy stuff, right? So the hypotheses almost write themselves if you just get used to the structure. The only thing that could possibly change is if you're trying to show that one's lower than the other, you make it less than. If you're just trying to show that they're different, you make it a not equal to. Same deal as we did with the 1 proportions. Shake your heads if you're okay so far. All right, so next step is, bless you, check conditions. Now, this is the least favorite part because it takes forever. Can you get through this? It's downhill from there. So we just got to live through conditions. Of course, on the upside, you know, they're pretty cookie cutter-ish, and we can nail these down on AP exam day and get that point. What's the first thing we check? Randomness. We didn't have a random sample. We already looked at that. We could hope that the patients they studied are representative of all such cardiac patients. That's what we're hoping for. So we're going to make an assumption about that. So let's say that we're going to assume that the patients in this study are representative of all cardiac patients. We don't have any reason to think otherwise. I mean, if the study was published in a professional journal, we would hope that the people who published it knew what they were doing. Okay. What else? See if they're independent. So this was the new one that we had to add for 2 groups. We need the depressed patients to not have anything to do with the non-depressed patients in terms of the rate at which they die. So we need to assume that those are independent things. So we're going to assume, they didn't tell us, but it's reasonable to think so. Assume that the death rate for depressed patients is independent. Is independent of the rate, maybe the rate for non-depressed. Got a little wordy there, but make sure context is clear. Make sure you use the complete sentence. Those couple of people out there who are still trying to take shortcuts and just say independent, groups are independent, and you're trying to take a shortcut, it's not going to pay off. You won't get points for that. Might as well just, put on your big boy, big girl breeches and write the whole sentence and be done with it. Okay, we want the point. All right, what else? The less than 10% condition. So this is to make sure that our sample size is not too big. Okay. So do you think maybe there's at least 3,600 non-depressed cardiac patients out there? I think that's reasonable. We think there's at least 890 depressed cardiac patients out there? Yeah. Probably. So I think the 10% condition is a pretty solid thing. So we'll argue that 361 and 89 are each less than 10% of all depressed and non-depressed cardiac patients. That's believable. All right, one last check. What do we do now? Okay, the NP-NQ is greater than or equal to 10. So this is to make sure that our sample size is big enough. So the one we just did is it not too big? And then the last one is it big enough? So that they're both about sample size. So let's see, we got non-depressed. So N sub N, P hat sub N is the counts for the non-depressed group. Now they gave us that number. There's no reason to reinvent the wheel on that one. They told us of the non-depressed people, 67 died. So this is 67. We already know that number. There's no reason to have to redo that. And then the N sub N Q hat sub N, which is the number of non-depressed people who didn't die. Technically those were failures, odd as that sounds. Was let's see, we had a total of 361, so 361 minus 67 is 294. Okay, and I think that's maybe easier than reinventing the wheel and doing 361 times 67 over 361 equals 67. That's just, if they give you counts, just go ahead and report them. It's easier. All right, now let's do the same thing for depressed. So N sub D, P hat sub D. So the number of depressed people who died was 26. Again, don't reinvent the wheel, just report it if you already know. And then number depressed times Q hat depressed. Well, let's see, there were 89 total, so 89 minus 26 is 63. So 63 of those lived. All right, there's a pause button. Here we go. All those are at least 10, right? So all successes and failures are at least 10. Check. Okay. So check, 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 check. A normal model is appropriate. What should we do? All right, so let's run a 2 proportion Z test. Okay, the worst is over. If you can get through conditions, the rest is way less unpleasant. All right, how are we doing so far? Any questions, comments, teardrops? Awesome. We'll cry later. We don't have time right now. Here we go. So, mechanics. So we checked conditions. That means we know that a normal model is appropriate. So I'm going to start with a picture because picture conveys a lot of stuff about the whole situation, and it's worth points. So those of you who don't want to draw a picture, you know, you're sacrificing maybe potential 4s, because if there's anything you forget to write down in symbols, sometimes the picture will cover your backside on that. So I think it's always worth. This is a picture of all possible sample differences, P hat D minus P hat N. So I'm going to label this differences P hat D minus P hat N. We only know one of those because we only had one study done. But if we did more studies and got more and more and more and more and more things, more numbers to crunch, we would get a picture that looks like this. And the mean, let's see, mu of P hat D minus P hat N, that's kind of messy, but that's the mean of this sampling distribution, the mean of that picture of all samples. Where is that? What number is there? Yeah. We said in the null hypothesis that the difference was 0. And that is where the middle of our model is, because the model is a reflection of what we're assuming in the null. So we're assuming that the mean of all possible samples, which is the mean of the population difference, is 0. So the middle is 0. Okay. Now we need a standard error, and that's where the things get messy with the pooling. So I've got to find the standard error pooled. And I'm going to leave off the p hat d minus p hat n because I don't really have room to squeeze it in here, and it'll be okay. So I need some pooled proportions first, and I usually go out in the margin and do that just because it makes this whole section messy. So let's go over here in the margin, and let's do p hat pooled. You do need to write the work out because if you make any calculation errors, you need work to cover your backside. You can still get full credit if your work's correct, even if your crunch your numbers wrong. And we are out to get as much credit as we can. Okay? We work too hard to not get our points. So we're going to put everybody into the pool. Everybody in the pool. That means we're going to take the 361 plus 89 people that we studied, and we're going to put that total on the denominator. So the denominator is the sum of all possible people. I did non-depressed plus depressed there, but it doesn't matter. You get the same number. And then we need the successes in the top. Well, let's see. We had 67 die in the first group plus 26 die in the second group. So those were our successes. So we take all the people who died over all the people we studied to get a p hat for everybody in the same group combined. If you crunch those numbers, you end up with about, where did it go? 0.206. It's a repeating decimal, 206 bar. And I'm going to try not to round, but if you round that to 207, nobody's going to bark at you. It'll be okay. It's just a model anyway. It's still wrong. We could have an unusual sample. It's just a model. So we're going to roll with it. So while I'm at it, let me go ahead and find Q hat pooled. So Q hat pooled is 1 minus this, which is 0.7. Can I subtract from 1? Oh, help me out. 793. Alright, so those are the p hat and q hat that I'm going to use in my standard error formula. So I'm going to kind of have those over to the side so I can just plug them in to my standard error formula. Alright, are we okay so far? It's a little bit of extra work, but from there, the rest of it is the same amount of work as it would have been if we hadn't pooled. So the worst really is over. So now we got to get our standard error formula filled in. That's the same formula that we used for the confidence intervals. So we have this big square root with a whole bunch of stuff under it. And in the first section, we're going to do, let's do our depressed first. So that's p hat pooled, so 0.2066666 times q hat pooled, 0.793333333 over sample size of the depressed. That was 89. Order doesn't really matter in this one because you're adding. And then you do the same thing for your second sample. So you use your p hat pooled again, 0.2066666 times 0.793333333 over the sample size of 361. Okay, so it's the same formula. You just have to use that pooled proportion for both of the numerators. Now, for those of you who've already been experimenting with the hypothesis test button on the calculator automatically pools. It's programmed to do so, which means if you forget to pool in your work, and then you use the shortcut on your calculator and they don't match, you're going to lose more points than if you just did it the old-fashioned way. So I would probably, especially for proportions, stay away from the magic hypothesis test button, because the worst thing that could happen if you forget to pool in your work is that the rest of your work matches it, and you might lose a point for forgetting to pool and still get a 3 out of 4. But if you run your hypothesis test on your calculator and it does a pool and you forget to show the work for pooled, you're probably down to a 2. It's probably not worth the risk. Because as long as your work matches the rest of the way through, the only thing you would lose credit for is forgetting to pool. And that's easy to forget, okay? But, you still get a 3. And threes are fabulous. We'll take them. Now that we have the standard error, we can, oh, no, we didn't finish it. That gives us, for those of us who don't want to actually type all that mess in the calculator, that's 0.048. You'll have to do it on your own later, so I'll cut you a break on this one. That's without anything rounded. So if you're getting something slightly different, it's probably because you rounded more than I did. Alright, so now we can do a z-score. So z equals, And we're going to start it just like we did in the confidence interval. We need the difference of the two proportions, depressed minus not depressed. So depressed, if I remember right, was 0.292, and non-depressed was 0.186. So that's the difference of the two observed proportions, which is the same thing you start your confidence interval with, minus, what do we expect the difference to be? 0. It's what's in the middle of that normal curve. That's always a 0. Over the standard error, which we crunched that up there at 0.048. For those of you who want to crunch that mess in the z-score formula, you can do that. As long as the work's there somewhere, it'll be okay. And once you get that all crunched out without round-off error, you should get a z-score of about 2.22. Is 2.22 standard deviations above the mean kind of unusual? Yeah, if you use a 5% alpha level, it is. So that's statistically significant. But we actually do need a p-value to argue that. So I want to know, if we go a little more than 2 standard deviations above the mean, how unusual it is to be that far from 0 or farther. That's a p-value. Okay. So I need the p-value, which is equal to the probability of a z bigger than 2.22. And how am I going to get that number? Normal CDF on the calculator. All right, sounds good to me. So grab your calculator, and we'll do menu, either probability or statistics, distributions, normal CDF. We want to go from 2.22 to infinity, which is about 0.013. So there's a 1.3% chance of getting a sample difference at least as big as 10.6% that we had, which is unusual. So 0.013. So what are we going to do with our null hypothesis? We're going to reject it if we use alpha level of 5%, which is pretty standard unless you're told otherwise. Yes, sir.
So do we need to repeat every time that we're going to use an alpha level of 5%?
Yes. So now that we know, so this is the last thing we need to kind of add in that we weren't doing before. Now that we know what an alpha level is, we will be expected on the AP exam to report the alpha level we're using to justify the decision that we make. You can do it one of two places. You can either write somewhere in these mechanics, just wherever you find a spot, you can write, I'm going to use an alpha equal to 0.05 or whatever you choose. Doesn't really matter where you put it. Or you can put it in your conclusion. I'm going to make a habit of putting it into my conclusion from now on, just to cover my backside to make sure it's there somewhere, because I might forget to write it in my mechanics, but I'm going to make it a habit in the conclusion. So let's conclude. Almost done. With a p-value of 0.013, we will, you already told me we're going to reject the null hypothesis at alpha equals 0.05. So I'm just going to tack it on to the end of that first sentence as a habit from now on to make sure I make a connection between my decision, my p-value, and my alpha level. We didn't do that before because we hadn't learned alpha levels yet. So it's a new component. We were using it, we just weren't saying so. Alright, so then the second sentence has to get the context. So if we don't believe the null, it means we believe the alternative, and the alternative said that depressed people were more likely to die than the non-depressed people. So I got to throw that in there. We have evidence that depressed patients are more likely to die from cardiac disease than non-depressed patients. Alright, how we doing? Any questions, comments, teardrops? Alright, one more slide and you should have about a half an hour to get some work done today. Use it wisely. So let's do this last little piece. I threw in, for your sake, another round of explain what the p-value means in context, because we still struggling with that one. And we will struggle with that one for times to come, and we'll keep rehashing it. So, the p-value means it's a conditional probability if the null is true, which says that the rate of death is the same. Alright, so if the death rates are the same for both groups of patients, the probability of observing a sample difference at least as large as the 10.6% observed in this study is 0.013. Digest that. Try not to throw it back up. It's rough. This is a real struggle. But it always is. Yes, sir.
So this problem, if it wasn't like about a difference and it wasn't a true proportion, you would exclude the word difference.
Yes. Pretty much. You got it covered. Alright, last question. If your conclusion is actually wrong, which type of error did you commit? Type 1. Okay, so why is it type 1? Well, we rejected, right? If we rejected and that was the wrong call, then the null would have been true. True null with a rejection is a type 1. So just we'll keep throwing these terms back in because we need to get more and more comfortable with them. The only way to do that is just to keep rehashing. And eventually we'll just talk the talk like it was their old usual language. Alright, you gotta practice some. Because this, you were not born doing this, and watching me do it one time is not enough to get you by on test day on Tuesday. So you're going to go to page 560, and you're going to take a whack at problems 31, 35, and 37. I left you about 30 minutes to work. Use it wisely. My work's hanging on the board, and it's in Schoology. I would strongly suggest you check your work, since we're not doing a quiz over this, for me to check your work. So you need to be looking at feedback on your own. All right.